Warm up for today. It said to draw a graph containing 10 points for each of the following situations. The first situation was if you had a strong positive correlation. Positive means that your dots should have gone up. You should have had 10 of them. And since it's strong, you want to make sure that they're all going up. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that would be a strong one. Yours might have gone a little bit more to the right, but again, every dot should be going up after each other. Second warm up said a weak negative correlation, so it still needs to have a negative trend, but it doesn't need to be as strong as the first one. So obviously we're starting off 3, 4, 5, 6, 7, 8, 9, and 10. The trend is negative, but it's not as strong, it's not as obvious, which would be a weaker correlation. Checking your answers from last night's homework with a practice in problem solving A-B. Number 1, this is what your scatter plot should look like. 2 was positive, 3 was negative, 4 was a positive relationship. As the temperature goes up, more people would get in the pool. Number 5, no correlation. It's not going to matter what age you study algebra and your height. Number 6 talked about hot chocolate. There was correlation because the colder it gets, the more hot chocolate they're likely to sell, but vendors would not cause the temperature to fall. It's just that they would sell more because people are cold. Today we're starting on 8.2, fitting lines to data. So we've already learned how to read a scatter plot, how to know if it's positive, negative, and if it has a strong correlation or a weak one. Now we're going to actually find a line of fit. When we talk about finding a line of fit, we are going to be putting it back into the equation y equals mx plus b, which means we'll be needing to find m for slope and b the y-intercept. So when they do have the strong relationship, we can find a linear model, and again that process is called fitting a line or finding a line of fit. So our Explore activity gives you a table listing the median age of females living in the United States. They want to know whether a linear model would be reasonable for the data, which means is there a strong positive or a strong negative? It's not going to make sense to draw a line for no correlation. Now, in order to not have such big numbers to deal with in the year, a lot of times what they'll do is they'll give you a statement such as, let X represent time in years after 1970 in this case. So that means we have to subtract each of those years by 1970. Well, if I subtract 1970 by 1970, that's going to be 0. 1980 minus 1970, that's going to turn into 10. 1990 will be 20 years since then. 2000 will be 30. And 2010 will be 40. So these are the numbers we're going to be using in our chart, not the 4-digit ones. So our X values will be 0, 10, 20, 30, and 40. The numbers in the right, the median age, we're not going to change those. So that will still be 29.2. 31.3, 34, 36.5, and last but not least, 38.2. So now they want you to make a scatter plot of it. So go ahead and create your scatter plot for point B and answer the question of, do the points appear to form a line or not? Your scatter plot should be filled in now, so let's go ahead and get mine filled in. So we're missing 35 in this box, 10, and then 30 in here. So we should have 0, 29.2 is going to be around here, 10 and 31.3, 20 and 34, a 30 and 36.5, and a 40 and 38.2. So your scatter plot should approximately look like this. And do the points appear to form a line? The answer to that is definitely yes. Next step, they want you to use a ruler and draw a line that passes as close as possible to the plotted points. And again, that's what they refer to as the line of fit. It does not necessarily have to pass through any of the points, but you should at least have the same number of points above and below. This is where it kind of gets a little challenging, and your line is going to look different than your neighbor's probably, because everybody eyeballs it just a little bit differently. My drawing won't be as straight because I don't have a ruler to use on here, but you all can borrow the ones in the class, or your calculator makes a great straight edge. And again, hopefully yours is a little bit prettier than mine. Now we need to find the equation of the line of fit. You generally want to use 2 points that your line has gone through. They're telling us what points to use so that way we can have the same answers. And you'll see that happen a lot. It just makes it easier to figure out if you did it right or wrong. So they're telling you to use 20, 34, and 50, 40. So the first thing we have to do is find the slope. So we take our y values and divide it by our difference in x values. Well, 40 minus 34 is 6. 50 minus 20 is 30. And just like when we did slope in chapter 6, we want to always simplify it. We can divide them both by 6. So the slope for this is 1/5. Then, just like we did a couple sections ago in Module 6, you take your slope, you take one of the 2 points, and again they're telling us to use 20, 34. Remember, it wouldn't matter if you use the other one, because it would come out to be the same thing since they're on the same line. And we start plugging it into y equals mx plus b. 20, that's our x. 34 is the y. And again, m we already said was 1/5. So we now have 34 equals 1/5 times 20 plus b. If you don't like the boxes, you don't have to write in them. There is some space on the sides if you want to just get rid of the boxes. Well, 34 is now equal to 4, 1/5 of 20, or you could think of it as 1/5 times 20 over 1, ends up being 20/5, which turns into 4. To solve for b, we now need to subtract the 4. So our b value is 30 here. So now that we have m and we have b, we can write our equation, which is y equals our slope plus our b value, which is 30. So we have 3 reflection questions here. Go ahead and answer them within your groups, and then unpause to make sure that you were on the right track with your questions. The slope of the line of fit tells you that at about every 5 years, because that's your x values, the median age of females goes up by 1. The y-intercept of the line of fit, it tells you about the data. Well, it's where it started. It's where they started surveying, where they started collecting data. And the last question, how does the slope of line of fit relate to the type of correlation? Well, we knew the points were going up. If you look at your slope is also positive. So it's a positive correlation. Which means the slope is positive. So that's one way to check yourself, as just a quick check. If you have a positive correlation, your slope should be positive, and if you have a negative correlation, the slope should be negative. Now, because data is a real-life situation, it doesn't mean that you'll always have a line of fit, and then some lines will fit it better than others. So we need a way to evaluate that, which is what we refer to as a residual. A residual is the vertical distance between the data point and a line of fit. After you calculate residuals, you can draw a plot. This is not your scatter plot, this is an additional graph. And it allows you to see, are the residuals close together? Are they on both sides of the line? Making sure that your line of fit accurately describes the data. So they've given you 3 types of distribution of residual plots below. The first one, notice you've got some above the line. You've got 3 below, same amount as above, and then this one in the middle. Because you have it, it's random and tight, it's not loosely scattered. This one means that the line of fit was well. This one, you've got, again, the same number of points on top and on bottom, which is good. But they're a little bit more scattered. They're not as tight around that line. So while it's a good line, it's not the best. The third one, you've got 4 points above it, 2 points below. This one's not a great fit at all. So you would actually want to redraw the line of fit if these ended up being your residuals. So example 1, they've walked you through an example of finding residuals. The first 2 columns is directly imported from the table. So if you look back at our example, our Explore activity, you'll notice we changed the years from 1970 to 2010 to the years 0, 10, 20, 30, and 40. So we just replaced them here. And then our Y values, which we call the actual ones because they were the actual information that we collected, went here. Now I evaluate the quality of our line by using its equation to find predicted values. So the third column to create this one, we substitute x. into our equation. And then to find your residual points, as it tells you, you just simply subtract straight across. So you're going to subtract 29.2 and 29, 31.3 and 31.5, the 34s, the 36.5s, and then the last row. Now notice that some are positive and some are negative, so you take the actual y minus the predicted y. And again, notice that word from, so it's actual minus predicted. We're now going to plot those residual numbers. So when we had an x value of 0 in the chart, the residual ended up being a positive 0.2. And if you need to, you can flip back to the table. So that means year 0 was 0.2, so that's going to be in between here. We then went to year 10, and the residual ended up being a negative 0.2. The next 2 years, 20 and 30, were both at 0. And the last one, year 40, was at negative 0.8. So that one kind of throws our residual plot off there. Overall, to evaluate the quality of it, the residuals are all small. They're tightly distributed. Again, we do have that one kind of oddball, but one oddball is better than the majority of them being oddballs. So we'll say that this is a pretty appropriate model here. So if you're comparing two lines of fit for the same data set, how do you figure out between the size of the residuals which one's the better model? Well, you want the smaller residuals. And then the question says, suppose you know that your linear model is a good fit for the data set. What would the expectation of the residual plot look? Go ahead and describe what that would look on your paper. You would expect the residual plot to be tight and close to 0. We're going to be doing an example together. We're going to be creating a table for the residuals, so you might want a piece of paper out, unless you think you could create the table within the lines here. That's up to you. I've got some more space here that I can work with. So if you're going to take a piece of paper out, go ahead and do so. So we're starting back at the same table from the beginning of the problem. So I'm going to go ahead and list my first two rows here. So we have x, we have the actual y, our x values were again 0, 10, 20, 30, and 40. And again, I'm getting these numbers from, again, either the chart that they rewrote on 257 or the one at the very beginning on page 255. The actual y's were 29.2. Our actual y's were 29.2, 31.3, 34, 36.5, and 38.2. The third column will be the predicted, which is the y equals 0.2x plus 29.2. And then the last column will be the residuals. Well, again, to find the predicted, we take each of our x and we plug them into our y equals. I will do the first one with you, and then you can finish the rest in your group. I'm going to do that below here. So the first value that I'm going to plug in would be 0. So it's going to be y equals 0.2 times your x, which is 0, plus 29.2. Well, 0.2 times 0 is 0. 0 plus 29.2 means the first predicted value would be 29.2. Go ahead and finish filling in the table using your values of 10, 20, 30, and 40, and then unpause to double check that you got them right. Again, talking it over with your groups as needed. When you plug 10 in, you should have gotten 31.2. The next one was 33.2, 37.2, whoops, sorry, nope, sorry. This one would be 35.2, and then 37.2. So there's your predicted. So again, the residuals, we subtract the actual minus the predicted. So 29.2 minus 29.2 tells us the first residual is 0. So we're doing good so far. So go ahead and calculate the other 4 residuals. The next residual should be at 0.1. Then we have 0.8, 1.3, and then 1. So the first two looked great, and now they're starting to get a little bit too big. So now we're going to take the x values and the residuals and plot them onto our graph on the right. The first one's pretty simple. X was 0, residuals was 0. So 0, 0. The next one again looked great. We were at 10 and 0.1. But then the numbers started getting pretty big, 20 and 0.8, 30 and 1.3, and then 40 and 1. Well, we want an even distribution for it to be a good line of fit. And as you can tell, all the dots are above the line except for that one that's on it. Plus the residuals get quite big. So this is not a good fit for a line. So again, 2 residuals are big. They are not evenly distributed because they're all on top of the line. And that means the line is not a good fit. This last part that we're going to go over really is nothing new based off of what you have already done. It's just what we refer to as making predictions, which we did already using the equation. The difference here is that there are 2 types of differences you could make. So you might want to pull a highlighter out here. The first type is what we call interpolation, which means you're making a prediction based on a value within the model's domain, which is why the word inter here. So with our column, we had between 0 years since 1970 and 40 years after 1970. So any x value that's between 0 and 40 would be within that domain. So we would call it interpolation. If you choose a number outside the domain, so that would be 50 years after 1970, 100 years, things like that, we refer to that as extrapolation. Extra, think of it as extra information. You actually don't have that data. So example 2, again, we're still using that same data table back from the very beginning of the lesson. We have the equation y equals 0.25x plus 29. And they want you to use the model to predict the median age of females for 2 years. The first year of 1995 and then 2015. Well, remember, we are not actually using those 4-digit years anymore. We're using since 1970, so we subtract. Well, the difference between 1995 and 1970 is 25 years. So this becomes my x value that I'm going to plug into the equation. So they said 0.25 times x, which is 25, plus 29 is an average age of 35.3. Since the year 25 is between the data in the chart, which is between 0 and 40, that is an interpolation information. The second year they ask us to find is 2015. So again, we take 2015 minus 1970. So the x we're plugging in this time is 45. So we go back to the same equation, and we go 0.25 times 45 plus 29 means that this age, median age, is around 40.3 years. Now 45 is past what our data included in the table because we ended at 40, so that means this prediction was extrapolation. So number 7, we know that if we're looking at the median age in 1995, that is your interpolation. And if they're using the year 2033, that's extrapolation. And the only information they're basing off of is the data in the table at the beginning, which went from year 0 to year 40. And they want to know which of their predictions is more likely to be accurate. So talk about this with your group members and then see if we all agree. Since 1995 is within that data, that means the line of fit would probably describe it pretty well, whereas in 2033, things could really change. So 1995 would be the more accurate prediction. Um, 2033 is far away from the data collected. We have 2 questions to wrap class up with today. We're using that same linear model, y equals 0.25x plus 29, and again, x is the number of years since 1970, and we're going to predict 2 years of the median age below. Once you've predicted them, also state whether it's an interpolation or an extrapolation. So go ahead, answer 8 and 9, and then unpause to figure out if you were all correct. Well, the first thing we have to do is take these years and subtract from 1970. So 1989 minus 1970 means we're actually using an x value of 19. So that's what we're plugging into the equation. So y equals 0.25 times 19 plus 29. So you should have had a median age of 33.75. Now our x value of 19, that's within the data range because we went from 0 to 40. So that means this is interpolation. So there's your two answers for number 8. The second question, we're using the year 2022. So I subtract that by 1970, and my x value is 52. So I plug that into the equation, y equals 0.25 times 52 plus 29. Multiplying that into the equation and then adding 29 to that tells us the median age would be 42. Well, if I look at my x value of 52, and I think back to my chart, I went from year 0 to 40. 52 is past 40, so that means this was extrapolation. We covered a lot in this section. You're going to have 6 problems for homework, and they're kind of walking you through it. And then tomorrow in class, you'll have the entire class to practice on some more, because I know it was a lot of information today.